Now we'll talk about linear approximation. So we introduced the linearization. This is a certain function that we can set up from a given function at a point. And the first use that we saw for it was to be equation of a tangent plane. Here's the second use. So we're going to use the same linearization for a second purpose, which is linear approximation. So the core idea, the key idea here is that if f is differentiable at a point AB, then for nearby points, for any point that's near AB, f of xy is approximately equal to L of xy, the linearization. So this L linearization is a linear function and it's approximately equal to f, hence the name linear approximation. This might remind you of some things from single variable calculus like Taylor polynomials or tangent line approximation. If you have a function that could be really complicated, but at a given point, the nice simple tangent line is a good approximation near this point. It's maybe not a globally good approximation. Out here, the function is way different than that tangent line that goes way down, or over here on the right, the function is way different from this tangent line that goes way up. But near this original attachment point, as long as you stay close by, it's a good approximation, and this straight tangent line is way simpler than that wiggly thing that's drawn there. Well, same thing for multivariable linearization. This linearization is a very simple function, right? We wrote down a simple formula for it, and it's a good approximation to f, as long as we don't go too far away from point AB. So, for example, if we wanted to find the square root of 1.12 plus 1.89 cubed, one approach that we could take is we could say, look, 1.12 is pretty close to 1, and 1.89 is pretty close to 2. And for any point that's close to 2, the function, well, it's z is written here. Z is supposed to be square root of x plus y cubed, I guess, right? For the z. That's going to be approximately equal to the linearization that we found earlier in our discussion. 3 plus 1/6 x minus 1 plus 2 times y minus 2. Well, 3 is 3. X minus 1 is 0.12. 1.12 minus 1 is 0.12. 0.12. And then y minus 2 is 1.89 minus 2. That's negative 0.11. So then just doing a little bit of arithmetic, we have 3 plus 1/6 of 0.12, that's 0.02, plus 2 times minus 0.11, that's minus 0.22. So 3 plus 0.02 minus 0.22, when you add it up, it comes out to be 2.80. That's the linear approximation for this value. If you put this original expression, square root of 1.12 plus 1.89 cubed, if you put that into a calculator and got more decimal places, you would get 2.805578 and then some more decimal places. So our linear approximation was pretty good. It got 1.5, almost 2 decimal places of accuracy, right? The rounding would probably be 2.81 instead of 2.80, but it didn't round up by a whole lot. It just barely rounded up. So this is a good approximation. Obviously, you know, if you're in a high precision setting and you need more than 2 decimal places, maybe you need to go beyond linear approximation. But look at what, you know, when we lose all the, you know, the massive accuracy, but look at what we gain. This was so simple. We did not need a calculator to find this linear approximation. It is a very simple procedure and a simple outcome, right? We had to compute some derivatives, and we found the 1/6 and the 2, but that's it. So in the trade-off of simplicity versus accuracy, the linear approximation is relatively simple and yet still maintains some amount of accuracy. Of course, you can go on further and do more sophisticated things, you know, add more terms to get more accuracy, but for now, it's the linear approximation. That's what we're looking at. I guess in some philosophical sense, this calculator value is not really an exact answer either, right? Because the calculator is only going to give us a finite number of decimal places. Maybe it'll give us 10 or 15 or 20 decimal places or whatever, but it's still only an approximation. Okay, so that's the basic idea of the linear approximation. You have something you want to figure out. You identify that this is square root of x plus y cubed, where x is 1.12 and y is 1.89. And that's close to the point 1, 2, which looks simpler. So we decide to use a linear approximation where f of xy is square root x plus y cubed, and we're going to use the point AB is 1, 2, and then the point that we're really interested in, 1.12, 1.89, is close to that simple point. 1, 2 is a simple point, or at least it's way simpler than the one we're really interested in. Okay, so we're writing down a function that fits the question, and then we're deliberately choosing a different point. We're choosing a different point that's simpler than the one that we're actually looking for. That's how we would use linear approximation for something like this. Here's an example for our function f. This is not the function f from the previous slide. This is a different function f. We're not given a formula. All we're given is that f of 3, 4 is 6, fx of 3, 4 is 5, and fy of 3, 4 is negative 2. Given that, what is an estimate for f of 3.1, 3.9? Is it 6.3, 9, 6, or 6.7? Which of those is the best estimate? You can pause the video and think about it. Well, f of 3.1, 3.9 would be approximately the linearization of 3.1, 3.9, which, according to the information we have, would be f of 3, 4, 6, plus the x derivative, 5, times x minus the x coordinate of the point 3. I'm going to use the linearization at the point 3, 4. I'm using point 3, 4 because we're given all this stuff about 3, 4, and the point that we really want is close to 3, 4. So we're taking the x derivative at 3, 4, which is 5, times x minus 3. And I'm getting 3 from the point 3, 4. And then I take the y derivative, fy of 3, 4, which is negative 2, times y minus 4. And I'm getting 4 from the point 3, 4. I didn't really write it down. I'm supposed to set x to be 3.1, and I'm supposed to set y to be 3.9. I just wrote down L of xy, but I'm supposed to plug in 3.1, 3.9. So let's see, we get 6 plus 5 times 3.1 minus 3 makes 0.1. And then negative 2, y is 3.9. 3.9 minus 4 makes minus 0.1. So let's see, I've got 6 plus 0.5, and then here the minus signs cancel out and we get 0.2. So 6 plus 0.5 plus 0.2 makes 6.7. And that's choice D. So based on the information we were given, our best estimate is 6.7. Let's try doing another estimate. Let's estimate, it's similar to our previous example, but it's not quite the same. It's a square root of 5.8 cubed plus 6.2 cubed. The previous example didn't have a cube there. So let's use f of xy is a square root of x cubed plus y cubed. What we want is f of 5.8, 6.2. So plugging in 5.8 for x and 6.2 for y. That's what we actually want. But somehow we're trapped on desert island without a calculator, and we would like to figure this out without a calculator, or we would just like to do it for ourselves. So can we do it? Well, there's a nearby simple point to the point 5.8, 6.2. Something nearby to that is 5, 6, or rather 6, 6. 5.8, 6.2 is close to 6, 6. 5.8 is close to 6, and 6.2 is also close to 6. So we could say f of 5.8, 6.2 is going to be pretty close to f of 6, 6. Square root of 6 cubed plus, 6 cubed. 6 cubed is 216. So we get 432. And let's see, what's the square root of that? It should be let's see, this is 2 cubed times 3 cubed times another 2. So I have 2 to the 4th times 3 cubed, and the square root of that would be 4 times 3 times square root of 3. 12 square root of 3. Right, the square root of 2 to the 4th is 2 squared, so I have a 4, and the square root of 3 cubed would be 3, so 4 times 3 makes 12, but there's 1 3 left over, square root of 3. And sure, I have a nearby point, I get a nearby value, but maybe we can do better. If f was a constant function and it was the same everywhere and there was no tilt to it, then when we moved xy, when we moved a little bit to the west and a little bit north, and everything was flat like Kansas or whatever, then we would be at the same height. But I mean, realistically, this graph is going to have some tilt to it. So if we step a little bit to the west and a little bit to the north, it's going to tilt up or down, and we should try to get a better estimate. So all right, enough discussion, let's just do it. let's use the linear approximation or the linearization at the point 6, 6. Then I gotta figure out some derivatives. All right, so we already figured out that f of 6, 6 is 12 square root of 3. And then the x derivative is 1/2 x cubed plus y cubed to the minus half times 3x squared. So in other words, 3 over 2 x squared x cubed plus y cubed to the minus half. And fx of 6, 6 would be 3 over 2 6 squared over, x cubed plus y cubed to the minus half is the thing we figured out before, 12 root 3. So I guess we could simplify a little bit. The one of the 6's cancels with this 12, and so we end up with and then the 2 from the 6 cancels with one of the 2's. So we end up with 9 over 2 root 3. For the y derivative, taking the partial derivative, we get 1/2 x cubed plus y cubed to the minus half times 3y squared, or 3 over 2 y squared x cubed plus y cubed to the minus half. And fy of 6, 6, well, it's actually going to be the same thing, right? These derivatives are the same except with x versus y, but x is 6, y is 6. I'm going to plug in the same number in the same place. I'm going to get the same value. I mean, I'm not saying that they're always the same everywhere, just that at the point 6, 6, because the x and y are the same, we get the symmetrical values. I should probably do a small simplification there. Okay, so L of xy ends up being 12 root 3 plus the fx slope, 3 root 3 over 2 times x minus 6, plus 3 root 3 over 2, the y slope, times y minus 6. And that means that f of 5.8, 6.2 is approximately equal to L of 5.8, 6.2, which is 12 root 3 plus 3 root 3 over 2 minus 0.2 plus 3 root 3 over 2 times plus 0.2. And look at that. Those two terms end up canceling out. No. Those two terms cancel out because there's a plus 0.2 and a minus 0.2. This is just 12 root 3. And 12 times square root 3, if you wanted to put that into decimals, that's approximately 20.7846, whatever, ... So that's what we end up with. So for one thing, after all that, we ended up with our original approximation. Well, that's life. In this example, it was set up so that the x change and the y change perfectly balanced out. So they just happened to cancel out. But I hope that the process made sense. In case you're curious, a little bit more decimal places on this square root. If you did it with a calculator, you'd end up with an approximation like 20.81922 dot dot dot. Okay, so comparing our simple linear approximation 20.78 versus 20.819, it's close. It got 2 significant figures, 20, and it was close on the third one, just a little bit off. So a pretty close approximation. So again, I hope that procedure made sense. The last topic in this section is about differentials, the differential of a function. The differential of a function is this expression that's written here. df is partial f partial x times dx plus partial f partial y times dy. And we'll see some examples in a second. The point here is that the linearization or the linear approximation could be rewritten to say f of xy minus f of ab is approximately equal to partial f partial x times x minus a plus partial f partial y times y minus b. In the original equation for the linear approximation, the f of ab was on the right hand side, and if we subtracted that onto the left hand side, you'd get what's written on this slide. Now, this x minus a, this is just the change in x. Like if you started at a and you ended at a different value, then this difference would be how much x changed. And a common name for that is delta x. Similarly, this y minus b is the amount of change in the y value if you started at b and ended at some other value y. So that would be delta y. So to go back a slide, in that example, we started at 0.66 and went to 5.86.2. So the x value changed from 6 to 5.8. It dropped down by 0.2. So the delta x would be minus 0.2. Delta x is minus 0.2. And this one, the y changed from 6 to 6.2. Delta y equals plus 0.2. So those were the changes in x and y. The change in f here, we had, or the change in the z coordinate, it started out at a certain value f of ab, and then it ends up at a different value f of xy, and this amount of change, this is usually written as delta f. So we end up with an equation like delta f is approximately equal to partial f partial x times delta x plus partial f partial y times delta y. This is just another way of, oh, I wrote all that in gray. I meant to write that in green just to be a little more legible. Fix that. Yeah, so this is just rewriting the linear approximation. The change in f is approximately equal to the x derivative times the change in x plus the y derivative times the change in y. And now if we let delta x and delta y go to 0, and we took a limit or an infinitesimal, then this in the limit or the infinitesimal version, this would be written as dx and dy for a sort of infinitesimal version of delta x and delta y. And the delta f sort of infinitesimal version is df. When we go to that infinitesimal limit, the approximation gets sort of infinitely good, or the error dies away, and we get something that's exactly right. Df actually equals partial f partial x dx plus partial f partial y dy. With finite values for these deltas, you get some slight amount of error in the approximation, and you saw that in the previous example. Our linear approximation was not exactly matching. It only got about 2 or 3 significant figures, but infinitesimally these would be equal. I've just written something down for the differential, and what I've done so far is I've just tried to explain how that relates to the linearization and the linear approximation that we've been talking about. We started with the linearization and subtracted f of ab onto the other side, and then wrote it in terms of deltas, and said if we let those deltas go to 0 and become infinitesimal, we would end up with the differential. So that's how it relates to the previous things we've been talking about. Let's see an example. Let's write down the differential of the function that we've been using as our example, square root of x plus y cubed. So we found it before, but let's work it out again. The x derivative is 1/2 x plus y cubed to the minus half, and the y derivative is 3/2 y squared x plus y cubed to the minus half. And with that, we get the differential is df equals 1/2 x plus y cubed to the minus half power dx plus 3/2 y squared x plus y cubed to the minus a half dy. And that's it. That's the differential. I would say that's the differential in general. We left it with an x and a y in there. That's the differential in general. So with a xy in there. If we go to the point 1, 2, then df would be 1/6 dx plus 2 dy. These are the same. Fx of 1, 2 equals 1/6, and Fy of 1, 2 equals 2. The same ones that we found before. So here is written the differential in general at any point, just a formula for the differential at any xy point, and then the differential at one specific point. Now what this is telling us, let's look at the second one at the specific point 1, 2, 1/6 dx plus 2 dy. What this is telling us is that if we have a change in x, then f would change 1/6 as much. If x changes, then f would change 1/6 as much. Like if x increases by a certain amount, then f would increase 1/6 as much. And if y changes, then f would change 2 times as much. 1/6 times as much. 2 times as much. Double. This is just infinitesimal. It's only really valid like at that point. As soon as you move away from that point, then the graph of f might curve and the slopes might change. But at that point and nearby, this is what it means. Here's a question for you. Suppose we're given the information. This is not the same function f as in the previous examples with square root x plus y cubed. But suppose for this example that suppose for this question that fx of 3, 4 is 5, fy of 3, 4 is minus 2, and f3, 4 is 6. Which of the following is true for x, y near 3, 4? Is it true that f is more sensitive to changes in x, meaning that changing x by a certain amount would change f more than an equal change in y? Is it true that f is more sensitive to changes in y, meaning that changing x by a certain amount would change f less than an equal change, making that same change in y? Or is it true that f is about equally sensitive to changes in x and y, meaning that changing x would change f about the same as an equal change in y? What do you think? You can pause the video and think about it. The answer is A. The answer is A. F is more sensitive to changes in x. If I change x by 1 unit, then this given information is telling us that a 1 unit change in x would lead to approximately a 5 unit change in y. Or, a 5 unit change in f, in the output value. Increasing x by 1 unit would increase the output value by 5 units. In contrast, if I made a 1 unit change to y, if I increased y by 1 unit, then the output value f would change by 2 units. It would decrease by 2 units. So the 5 unit change is a bigger change than the 2 unit change. For the purpose of this question, we're not worried about whether it's a plus or a minus. That's not what this question is about. This question is just asking about the amount of change. And a 5 unit change is a bigger change than a 2 unit change. So that's what it is. It's more sensitive to changes in x, at least in this region near 3, 4. At a different point, maybe the curvature tilts it in a different way, and it might be a different story. But at this point, that's what's going on. If you think about it, you can probably imagine why people might care about this, why it might be useful to know about this kind of sensitivity stuff. You might be in a situation where you can control variables x and y, and or at least measure them, and you're interested in the value of f. So if you're in a control scenario, well, the sort of two basic ideas are either you want to control it to keep f the same, in which case then y is apparently not going to mess it up too much, but you have to worry about x, because x is going to mess up your value of f that you're trying to keep the same. So you better keep a tight control on x. Or conversely, you don't want f to stay the same. You're trying to change f. And in that case, the sensitivity to x is not a problem. It's good for you. You like the fact that it's sensitive to x. You can change x a little bit and it will change f. So whether it's good or bad depends on your goals. Are you trying to keep f the same, or are you trying to change it? But knowing this this sensitivity enables you to work towards the control that you're trying to get. it also it might not be a control situation, it might be a measurement situation. You're measuring x and y, but unfortunately the measurements might have some error bars on them. That there might be some error bar on x and on y, and you're trying to use your measured values of x and y to figure out f. Well, according to what we're saying here, if the true value of x is a change from your measurement, that's going to make a big difference in the value of f, much bigger than y. So if running the experiment is very expensive or takes a long time, then and you have to choose where to devote your resources, say, just hypothetically, you could spend your money to measure y more precisely, or you could spend your money to measure x more precisely. Which one is worthwhile? Well, because of the sensitivity in x, if you can get the value of x more precisely, that's going to make 5 times as much difference to the value of f. So this sensitivity tells you where to allocate your resources in an experimental measurement setting. Imagine something like clinical trials of an experimental medicine or vaccine or something. Running clinical trials takes a long time and it can hurt people and it's very expensive. So knowing this kind of sensitivity can make a big difference. Well, that's it. Thanks for watching. Bye.